Welcome to The Explainer. Today, we are about to embark on what I genuinely believe is one of the most fascinating, mind-bending journeys the human mind has ever undertaken. We're going on a macro to micro journey, literally peeling back the layers of reality itself. We're going to start from a historical, groundbreaking moment, the famous gold foil experiment, and we are going to zoom all the way down into the absolute fundamental building blocks of the universe. I'm talking about quarks. Whether you're a dedicated student preparing for your physics papers or simply a focused learner hungry for the secrets of the cosmos, mastering this material is absolutely crucial. We're going to take complex ideas, chip away the confusion, and reveal the masterpiece of the subatomic world. And before we dive into the core of the atom, I want to quickly remind you to subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Let's get started. Here is our roadmap for today. It's a lot of ground to cover, but we'll take it step by step. First, we'll look at the nuclear atom model. Second, elements and isotopes. Third, radioactive decay. Fourth, a really fascinating story called the neutrino mystery. And finally, we'll dive deep into quarks, leptons, and hadrons. Okay, let's dive into Section 1, the nuclear atom model. This is where our journey into the microscopic world really begins. Let's travel back to 1911. We're looking at one of the most elegant and revolutionary experimental setups in the entire history of science, Ernest Rutherford's alpha particle scattering experiment. So picture this. Rutherford and his team took a radioactive source that was emitting a beam of alpha particles. They passed it through a collimator, which is basically a lead slit, to create a very narrow, highly focused, invisible beam. Then, they fired this beam at an incredibly thin sheet of gold foil. Surrounding this entire setup was a circular fluorescent screen that would produce a tiny, faint flash of light whenever an alpha particle hit it. Now, the results they got were absolutely astounding. The vast, overwhelming majority of the alpha particles passed straight through that gold foil with virtually no deflection at all. None. It was as if the gold foil wasn't even there. But a very small number of particles ricocheted off at wild, unexpected angles. Let's break down exactly what those deflections meant, because this brilliantly illustrates Rutherford's massive realization. When I say a small number, I mean only about 1 in 10,000 alpha particles were deflected through angles in excess of 90 degrees. Think about that fraction for a second. It's minuscule. Now you have to remember what alpha particles actually are. They are positively charged, and they have a mass about 8,000 times that of an electron. They are the heavy artillery of the subatomic world. For a fast-moving, massive alpha particle to just bounce straight backwards, it couldn't possibly just be hitting a soft, diffuse cloud of positive charge, which is what scientists believed the atom was at the time. That large-angle deflection could only occur if the alpha particles slammed into an object significantly more massive than themselves. This led to a complete paradigm shift in physics. Rutherford concluded that all the positive charge and virtually all the mass of the atom must be concentrated in a tiny, incredibly dense core. He developed the solar system model of the atom, where this massive positive nucleus sits right in the center, surrounded by mostly empty space, with tiny negatively charged electrons orbiting far, far away. Moving right along to Section 2, elements and isotopes. Now that we know the nucleus is there, we need to zoom in and see exactly what lives inside it. All right, let's meet the core subatomic players. The nucleus of an atom has a structure primarily made up of protons and neutrons. A proton carries a positive charge of +1 e, where e is the elementary electronic charge, and it has a mass of 1 unified atomic mass unit, or simply 1u. The neutron, true to its name, is totally neutral. It has 0 electrical charge, but it shares that exact same mass of 1u. Both of these heavy hitters reside firmly inside the nucleus. Now compare that to the electron. The electron sits out in the outer atom, orbiting in that vast empty space. It has a negative charge of -1 e, which perfectly balances the proton's positive charge. But look closely at its mass, 1/1840 u. The electron is incredibly, almost incomprehensibly tiny. You would literally need nearly 2,000 electrons just to equal the mass of a single proton. This perfectly reinforces Rutherford's discovery. Almost all the mass of everyday matter is locked tightly in that tiny central nucleus. So, how do we catalog all these different atomic combinations of protons and neutrons? Well, we use standard nuclide notation. Take a look at this notation for chlorine-37. This is absolutely vital for your foundational understanding, especially for your exams. The bottom number, the 17, is the proton number. Think of this as the ultimate identity card of the element. The number of protons determines the element's chemical properties because it strictly dictates the number of outer electrons. If a nucleus has 17 protons, it is chlorine. Period. End of story. The top number, 37, is the nucleon number. That's the total number of protons plus neutrons packed into that specific nucleus. So the crucial point here is understanding what isotopes are. Isotopes are just different forms of the same element. They have the exact identical number of protons, which means they have identical chemical properties, but they have different numbers of neutrons. For example, to find the number of neutrons in this specific chlorine-37 isotope, you just do a bit of simple math. Subtract the bottom proton number from the top nucleon number. 37 minus 17 gives us exactly 20 neutrons.
Section 3. Radioactive decay types. Let's shift our narrative to what happens when these tightly packed nuclei get a little too unstable and literally start breaking apart.
Let's methodically compare the four most common types of decay that occur when a nucleus becomes unstable and needs to release energy. First up, alpha decay. The nature of an alpha particle is essentially a fast-moving helium nucleus. That's 2 protons and 2 neutrons tightly bound together. Because of this composition, it carries a hefty charge of plus 2e. Due to this high charge and its relatively massive size, it interacts heavily with any matter it passes through, causing massive ionization. Therefore, its actual penetration power is very weak. It loses its energy incredibly quickly and can be stopped by just a few centimeters of ordinary air, or even a single thin sheet of paper. Next, we have beta-minus decay. This is a very fast-moving electron that gets violently ejected straight from the nucleus, carrying a charge of -e. It's much smaller and faster than an alpha particle, so it has fair penetration. It can get through paper, but will be stopped by several millimeters of aluminum. Then, we have a really fascinating one, beta-plus decay. This emits a fast-moving positron. Now, a positron is an antiparticle, specifically an anti-electron. It has the exact same mass as a normal electron, but it carries a positive charge of plus e. Its penetration is uniquely weak, but for a very dramatic reason. The moment this free positron collides with an ordinary electron in the environment, the two particles completely annihilate each other in a flash of pure energy, producing high-energy photons. Finally, gamma decay. This isn't a physical particle in the traditional mass sense. It's short-wavelength electromagnetic radiation, pure energy. It has 0 charge and 0 rest mass. Because it rarely interacts to ionize other particles, its penetration power is incredibly high. It passes through almost everything and is only partly stopped by several centimeters of dense, heavy lead.
Now, when these decays happen, they don't just happen randomly. They follow strict, unyielding mathematical rules. I want you to think of balancing a nuclear equation exactly like balancing a strict accounting checkbook. Absolutely nothing can be lost or unaccounted for. Here are your 3 basic steps. First, identify your starting nucleus and the specific particle being emitted. Second, you absolutely must conserve the nucleon number. That means the superscripts, the top numbers on the left side of your...
Right, let's move to Section 4, the neutrino mystery. This is where the story of physics gets a little dramatic as we introduce a historical anomaly that utterly baffled the brightest minds in the world.
I want you to look closely at the slide. Specifically, the graph on the left. We have the energy spectrum of alpha particles emitted from a specific radioactive isotope. Notice those sharp, distinct, vertical spikes. Those spikes tell us that the alpha particles have specific, quantized energies. And honestly, this makes total sense. It means the energy levels within the nucleus itself are discrete, much like how electrons sit in discrete energy levels in the outer atom. When an alpha particle breaks off and leaves, it takes a very specific, predictable chunk of energy with it. But now, shift your attention to the graph on the right. This is the energy distribution when a sample decays by beta emission. It is not a sharp spike. Not at all. It is a broad, smooth, continuous, and frankly, messy curve. Some beta particles come flying out with lots of energy, some come out with very little, and most are somewhere in between.
This single observation caused absolute panic in the physics community. Let's think about why. If a nucleus drops from one specific energy state to a lower specific energy state, the total energy released should be a fixed single value every single time. So I'm going to pose this exact question to you to really think about. Why is the beta particle energy distribution continuous? If the total energy released in the decay is a fixed amount, but the beta particle we measure is only carrying away a random varying fraction of it, where in the universe is the missing variable energy going? It genuinely seemed as though the sacred, unbreakable law of conservation of energy was being broken.
The brilliant resolution to this crisis was the bold proposal of a ghost particle. To save the foundational laws of physics, scientists realized there simply had to be a second, completely invisible particle being emitted alongside the beta particle. This ghost particle was quietly sneaking away with the exact remainder of the missing energy. And that is exactly what the neutrino is. The neutrino and its antimatter counterpart, the antineutrino, are bizarre little particles emitted in beta decay that have exactly zero charge and virtually zero rest mass. They perfectly share the available energy with the beta particle. If the beta particle takes a little energy, the neutrino takes a lot. If the beta particle takes a lot, the neutrino takes a little. The sum is always constant. And there's a beautiful, elegant symmetry here balancing the matter and antimatter scales. In beta minus decay, where a normal matter electron is emitted, an antimatter antineutrino goes with it. In beta plus decay, where an antimatter positron is emitted, a normal matter neutrino accompanies it. The missing energy was found, the books were balanced, and physics was saved.
Which brings us to our final and deepest zoom in. Section 5. Quarks, leptons, and hadrons. We are going to crack open protons and neutrons themselves to reveal the absolute fundamental layers of our universe.
To even begin to understand this subnuclear realm, we have to categorize the massive particle zoo into two main families. On the left side of our slide, we have leptons. The word comes from Greek, roughly meaning the light ones. Leptons are believed to be truly fundamental particles. What does that mean? It means they have no internal structure. They aren't made of anything smaller. They are the bottom floor of reality. Electrons, positrons, neutrinos, and antineutrinos, they all belong to this exclusive lepton club. On the right side, we have hadrons, meaning the heavy ones. This group includes the protons and neutrons we've been talking about. The absolutely crucial point here is that hadrons are not fundamental. They have an internal structure. They are hiding a deeper secret within them, because they are actually constructed from smaller, truly fundamental particles. And what exactly are those smaller fundamental particles hiding inside the hadrons? They are called quarks. There are 6 types, affectionately referred to by physicists as flavors of quarks. We have up, down, charm, strange, top, and bottom. Now, I know these names sound incredibly peculiar, maybe even a bit silly, but I need you to focus closely on their mathematical properties, because this is where the subnuclear reality gets truly weird. Unlike electrons or protons that have whole, clean numbers of charge like +1e or -1e, quarks have fractional charges. It sounds impossible, but it's true. The up, charm, and top quarks have a charge of +2/3 e. The down, strange, and bottom quarks have a charge of -1/3 e. And of course, every single flavor has a corresponding antimatter, antiquark, with the precise opposite fractional charge.
So how did these strange, fractional quarks combine to actually create the solid, everyday world we see around us? Well, they form a specific class of hadrons called baryons, which are always, without exception, made up of exactly 3 quarks. And this brilliantly illustrates the elegance of the math behind our universe. Let's look at the internal structure of a proton. A proton consists of 2 up quarks and 1 down quark, U, U, D. Let's do the math together right now. An up quark is +2/3. Another up quark is another +2/3. That gives us +4/3. A down quark is -1/3. 4/3 minus 1/3 equals exactly 3/3, which simplifies to precisely +1e. The fractional math works perfectly to give the macroscopic proton its standard +1 charge. Now look at the neutron. It is made of 1 up quark and 2 down quarks, U, D, D. Let's add it up. +2/3 minus 1/3 minus 1/3. That equals exactly 0, a perfect neutral charge. It's incredibly satisfying when the deep, weird mathematics perfectly mirrors the observable reality of the universe.
Before we move on to our grand finale, I just need to briefly define the other main branch of the hadron family tree, just to complete your structural understanding of the particle zoo. While baryons are made of 3 quarks, we also have particles called mesons. A meson is a type of hadron made up of exactly 1 normal quark and 1 antiquark bound tightly together. For example, a particle called a kaon might consist of an up quark and an anti-strange quark. Now, because they mix matter and antimatter, they are highly unstable and don't last very long, but they are fascinating parts of the particle zoo. They prove the diverse, incredible ways quarks combine together to form different structures.
Okay, we are bringing this explainer to its narrative climax. We are going to tie everything we've learned today together by returning to the phenomenon of beta decay, but this time we are going to look at it through the microscopic lens of quarks. We said earlier that in beta minus decay, a neutron simply turns into a proton, spitting out a fast electron and an antineutrino.
But what is actually happening deep inside that nucleon? The mind-blowing truth is that beta-minus decay is not just a whole particle magically changing. It is actually a single quark changing its flavor.
Let's walk through the brilliant mathematical elegance of this subatomic transformation to see how the universe perfectly balances its books at the deepest level. Step 1. Prior to the decay, inside the neutron, we are looking at one specific down quark. Its charge is -1/3 e. Step 2. The transformation. For reasons governed by the weak nuclear force, that down quark spontaneously changes its flavor. It literally turns into an up quark. Step 3. The emission. To make this change happen and obey the laws of physics, it must release an electron, which has a charge of -1 e, and our ghost particle, the antineutrino, which has 0 charge. Step 4. Let's check the result. After the decay, we have the brand new up quark sitting inside the newly formed proton, which is +2/3 e, plus the emitted electron flying away, which is -1 e, plus the antineutrino at 0. +2/3 -1 equals -1/3 e. The total charge of all the pieces after the decay is exactly the same as the single down quark we started with before the decay. Total charge is perfectly, flawlessly conserved, even at the absolute deepest, most fundamental layer of reality.
To summarize this strict, beautiful rules of this subnuclear scale, we can look at the core takeaway. Matter literally shifts flavors to create the radiation we observe in the macro world. A neutron becomes a proton simply because one incredibly tiny down quark decided to become an up quark, shedding an electron and an antineutrino in the process. It's a kind of microscopic alchemy, dictated by the flawless mathematics of charge conservation. We've zoomed all the way from Ernest Rutherford firing heavy alpha particles at a simple sheet of gold foil, peeling back the atom to find the protons and neutrons. We've navigated past the ghost-like neutrinos and drilled right down to the bizarre fractional charges of quarks shifting flavors in the dark. Taking this whole journey really leaves you with a profound sense of awe regarding the physical universe. But it also begs a massive question. If we found quarks hiding inside protons, what deeper, unimaginably small subnuclear structures might still be waiting to be discovered beyond our current standard model? Are quarks truly the bottom floor, or is there another basement? Keep questioning, keep exploring, and remember, to help you navigate these complex concepts and ace your papers, make sure you subscribe to our YouTube channel AC Exams at acetheexams_IGCS to excel in your Cambridge examinations. Thank you so much for joining me on this incredible journey to the center of the universe. I'll see you in the next explainer.